So in this video, what I want to go through are some specific examples of batteries and electrolytic situations that you may or may not be familiar with. So the stuff that you've learned previously is going to kind of apply here in special situations. So when you charge a battery, whether it's your phone battery or your car battery, basically what you're doing is you're forcing the electrons to go in the opposite direction. So a battery is a galvanic cell, but if you charge a battery, you're actually doing the electrolytic version. You're driving the electrons back to the reactant side of the battery so that it can then run itself. So to do this, you need a higher voltage backwards than forwards. Otherwise, the battery is just going to keep running. And this is why something called an ammeter in your car often goes through, goes slightly higher while your battery's charging, and then returns to normal. In your car, the battery charger is called an alternator. If you have a dead battery, it could be the battery needs to be replaced, or it just could be that the alternator is not actually charging your battery appropriately. So keep that in mind as you start driving further and further away from home on your own. Some other examples of batteries, this is just what you're going to see, some common batteries that we have now, because let's face it, to use a Daniel cell battery like the two half reactions that we saw with the bottles of, or the beakers of solution and so forth, that's not really practical. You wouldn't want to hook up your phone to something like that and walk around with it because you'd spill everything. So common modern batteries basically have the cathode and the anode at the opposite ends, or on the outside versus the inside. So this is the typical dry cell battery. So the dry cell is referring to the salt bridge, where it's not liquid, but it's a moist paste made up of a bunch of ions. So again, you don't have to memorize these, but this is typically what a dry cell battery looks like. So the overall reaction could be something like, so this would be a zinc battery. Mercury batteries, again, you've got the layers, you've got the paste being the, shoot, got a message. You've got the, where was I? Salt bridge being a paste so that you don't have a lot of liquid involved, but obviously in mercury battery, those little button batteries have mercury in them, so they're a little bit dangerous. But once again, you've got the anode and the cathode. Do you have to memorize these? Absolutely not. Just to kind of give you some information. This is probably more interesting than this part. Car batteries are actually made up of lead. Both the cathode and the anode are lead reactions that go on. That's why car batteries are very dangerous if they leak and so forth. Car batteries are many individual cells in, parallel, because you want to add the voltage up to get a stronger voltage when you start your car. And here is the reaction for that one. Solid state lithium batteries, again, you've got the electrolyte in a very rigid paste being separated by, or the salt bridge in a very rigid paste, separating the anode and the cathode. Fuel cells are electrochemical cells in which you actually have to continually supply the reactants. So one of the very common type of fuel cells is actually taking hydrogen and oxygen and creating water. So again, you've got the anode and the cathode, but because you're constantly using up the gases in order to make H2O, the need to constantly supply, shoot, sorry, I should have quieted that. The need to constantly regenerate the reactants is always there. Okay, so corrosion is kind of a natural, it's not really a battery, but it's something that takes place very, very slowly. It happens under normal conditions, costs a lot of money because it causes things to deteriorate. So you've got iron in the presence of water will create rust because iron in the presence of water will undergo oxidation, and then the oxygen undergoes reduction. Oxygen gas is creating water and iron oxide to boot. So this is very expensive. How can you protect your metals from corrosion? Well, you could put a sacrificial electrode next to it. So that's a lot of times what they'll do if you have to bury a storage tank, or they'll do this at the naval yards where all the ships are stored. They'll have sacrificial electrodes attached to the metal so that the metal doesn't corrode, but the sacrificial electrode does. So magnesium wants to undergo this reaction much more readily than the iron of the storage tank does, or than the steel of the bottom of the boat does. So these sacrificial electrodes are designed to not to prevent corrosion of the surface. Another example, in your water heater. Water heaters would last for a very long time as long as the sacrificial electrodes are replenished. So to have your whole water heater replaced when all you have to do is replace the electrode is much more expensive. So again, these sacrificial electrodes are designed to keep the important part from corroding. And I think that is all we've got.